And I want to welcome everyone again to Advanced PASCO Capstone Capabilities. Over the next hour, we're going to take a look at some of the more advanced features of Capstone for data collection in various modes and analysis. So we're going to go through some topics today that will probably, or that aim to answer some common questions once you get past the fundamentals of using Capstone to collect data from sensors. Those questions might include, how can I visualize sound waveforms? Or what are the output jacks on my 550 or 850 interface for? They could also include things like, how do I analyze motion in a video? We don't have to just get data from sensors. We can also get it from videos that we or our students capture with phones, cameras, so forth. So we'll talk about that. And finally, throughout two of the activities today, we're going to take a look at how we can use tools in Capstone to transform data and combine such measurements into the types of measurements we ultimately want to analyze. So the agenda is to cover those topics like those in three activities. The first activity is going to take a look at sound analysis. The second, Ohm's law, where we're going to talk about outputs. And finally, video analysis in the form of a bouncing ball investigation. Now, after each of these activities, we're going to pause and answer any questions, although Alec will be monitoring that Q&A and answering questions there throughout. So ask questions as they come up, and if there are any that still need addressing after the individual activities, we'll go ahead and do that as a group. And then I'll extend these ideas and give you some more thoughts on things you could do with the new skills we're learning, the new advanced Capstone capabilities that we're introducing today through these three activities. Now, as stated in the description for this webinar, we're going to assume that you're comfortable with the basics of data collection in Capstone. There are some important topics there, and there are some resources linked to in the description of the webinar, this one, that will link you to some Get Started tutorials and a prior recording that we did last fall, kind of the introduction that segues into our advanced capabilities activity today. So, Alec, would you mind pasting those links into the chat? And they can jump right to it, or they can find it in the invitation to this particular webinar. So let us jump into sound analysis. So in sound analysis, we're going to answer questions like, how can we view sound waveforms and determine the sound's frequency? And to do this, we're going to use a piece of equipment called a wireless sound sensor. Here is that sensor on my tabletop. We're going to use this particular sensor. It doesn't require any interface. It's going to give us data about sound pressure levels, but the activity we're about to do could be done equally well with one of our universal interfaces like the 550 or the 850 interface pictured here, and an analog sound sensor, whether it's from our science workshop line, the CI line, or the self-identifying UI line. So the techniques we're going to learn in this activity apply across our interface and sensor lines. So let's jump over to Capstone and try to answer these questions. How can we view sound waveforms and determine sound's frequency? So this is the startup screen in Capstone, and I'm going to begin by turning on this wireless sound sensor by pressing its power button, and then go to the hardware setup panel in Capstone, where I'll wait for it to scan and see that this wireless sound sensor is available, confirming the ID number so I don't grab a neighbor's. I'll go ahead and click on it under the available wireless devices, and it should move up to the connected devices in just a moment. Now, one important thing to know about this wireless sound sensor, it actually has two different modes. One, which is on by default, is the one we want. That's to actually use it as a wave sensor, looking at sound pressure level waves. The other is we could switch it as an alternative and look at sound levels and decibels. But in this case, our question is about sound waveforms, so we'll leave the sound wave sensor on. I'll collapse the hardware setup panel, and I'm just going to begin, perhaps foolishly, we'll see, by clicking on the sensor data button, which is going to take the primary measurement, the sound wave, as a percent of the full scale, and give me a graph of that versus time. So I just want to stumble into this and see, is this going to work? If it doesn't, what solutions can we come up with using the more advanced capabilities of Capstone? So I'll notice that every sensor has a default sample rate for the wireless wave sensors wireless sound sensors wave measurements. It defaults to 1 kilohertz, and let's just hit record. I have some chimes here, and I'm going to hit one of the chimes. I'll hit the shortest chime to begin, and I just want to look at the graph and see if we're getting what we hope to get. If you have any thoughts as we get this data, share them in the chat with everyone. So I'll hit record. And then stop. And after my talking here, you can see I hit the chime, and well, what are we seeing? Well, we're seeing some amplitude, and we're seeing that amplitude decrease over time. That makes sense. Is this a good representation of the sound pressure level changes, though, when I hit that chime? I'm going to zoom in on the x-axis here so we can see the data points themselves. And here we are looking at a very much smaller time scale. And share your thoughts. Do you think this is possibly a good representation of those sound pressure level changes from the vibrations of that chime? I might think it's a little bit jagged. I'm also seeing what might be some aliasing here. I'm not hearing beats, but we're getting some sort of beat-like phenomenon. Both of those might lead me to wonder, well, am I actually collecting enough data? I don't actually know what the frequency of vibration is for this small chime, but I'm beginning to suspect that maybe 1 kilohertz is not a fast enough sample rate to capture whatever is happening there. So let me see how high I can go. For this particular sensor, it looks like it maxes out in the current mode at 2 kilohertz. Let's see if that makes any difference. So I'll press record again. And stop. And let's zoom in once again. Maybe a little less jagged, but I'm still seeing those beats. I'm still seeing very sharp peaks. Not quite what I'd expect for what should be a fairly nice tone coming from this chime. So the problem we're running into right now is that I can't sample faster. I think I need to go faster than 2 kilohertz, but I can't do that with this wireless sound sensor in the mode that it's currently in. Now, I said you could do this activity with a 550 or an 850 as well. And on those interfaces, say it's an 850, I could crank up that sample rate up to 10 megahertz, which has certainly got to be fast enough. But I'm very soon going to get an error message from Capstone that looks like this. It says something along the lines of, wait, the sample rate you've chosen, 100 kilohertz, 200 kilohertz, something like that, is much too fast to actually record that sensor data continuously. So it makes some suggestions. Try reducing the sample rate. Well, that's counter to our goal. Connect using USB, or setting recording conditions. So there are some parameters there that it suggests, but I'm going to show you a solution that I think is the best one for things that are happening very fast, a very fast phenomenon. So David suggests use a lower tone. Yeah, that could be one way to handle that. I'm going to show you a way, though, that would work across many different frequencies of sound. This is a sound wave sensor, and it seems like it's not working as we wish it to. And that's because we need a different approach to this. So I'm going to go to the File menu and choose a completely new experiment. I'll discard this file. It wasn't working out for us, but I just wanted to pose the question, how do we actually record some phenomenon that's happening very fast, faster than the sensor can record data straight? And I'll go to hardware setup, and because I didn't close Capstone, my wireless sound sensor is still connected. That looks good. It's still on the wave mode. One of the two solutions to this problem is going to involve the display that we select. I showed you the graph display the first time around. This time I'd like to show you that there's actually a graph-like display that isn't a graph display. It is called the scope. So I'll double-click scope. And first impression here is that, well, it looks like quite graph-like. I'll go ahead and choose that same measurement for the y-axis, the sound wave percent, so the signal as a percent of full scale. X-axis defaults to time, and it's looking promising. These are some pretty small time steps here, so I might be able to get some more detail. But if we look down here, I'm still maxed out here at 2 kilohertz. So a scope is only part of the solution to this. The main part of the solution is to recognize that I'm currently in a mode which is the default for new files called continuous mode. This means that when I hit record, a Capstone is going to try to gather data from the sensor at the sample rate continuously with no breaks. In this case, though, I need to go faster than this Bluetooth wireless connection would allow. And the way I can do that is by switching from the continuous mode to a mode dedicated, as the name implies, to monitoring very fast changing signals. It's called fast monitor mode. And if I choose fast monitor mode, you'll notice a couple of things. One is what was a record button becomes a monitor button. We'll see the ramifications of that in a moment. The other thing is a little more subtle. You may have noticed that I can now increase the sample rate for this sensor to above 2 kilohertz. In fact, let me see. Even though it's a Bluetooth wireless connection, I can go up to 100 kilohertz. Now, it turns out I'm going to leave it here because there's something very nice about using the scope display. If you look at the top of the scope display, not only does the scope display itself look like a graph, but there are buttons that you may be familiar with in the Capstone graph, like scale to fit and coordinates tools. But there are other tools here dedicated to the scope, and one of those very nice features is this button, which is on by default. It says automatically adjust the sample rate based on the time axis scale. So I don't actually need to pick a sample rate here. I can adjust the sample rate, as you can see, by adjusting the scope's time axis. So I'm just going to adjust that on the fly once we get a signal here. And since there's no record button, I will press monitor and I'll hit that chime again. Let's take a look at what we see in the scope display. All right, well, it's going to pick up my voice here in a moment, but I hope you saw that that looks much smoother. It looks like I'm doing a much better job at capturing the sound pressure level changes of that chime. So let me hit the chime again and be quiet. And I can make it smoother by stretching out that axis and the sample rate changes correspondingly. So let me go ahead and get a nice chime, nice sound waveform here. And you'll notice I press stop. The sensor is going to be monitored in the scope, and any data that came in previously just disappears. So if I want to capture something to look at in more detail, I'm going to press stop. And at least for the moment, I'm going to get that last trace in the scope. Well, how is the scope doing this? How is it accomplishing a sample rate of 100 kilohertz? Well, unlike the continuous sampling mode, it wasn't recording all of the data. It was merely asking the sensor for data at a very high sample rate, as much as could be fed to fill the frame of the scope. So basically one trace, and then it would ask for another one, and it didn't care about losing data between those different frames of data. So by using the scope and fast monitor mode, we can sample very quickly, in this case, 100 kilohertz from this wireless sound sensor, and look at phenomena that we couldn't record continuously. And it's this combination of fast monitor mode and the scope display that make this feasible. So what happens when you stop and you're monitoring? I'm going to open up the data summary to show you how this monitoring behavior works. Notice that what is normally a run name here is called monitor run. And if I were to hit monitor again, the current monitor run will disappear and be replaced by another one. So let me hit monitor and I'll hit the chime again. And you notice that each time I hit monitor, I get a new monitor run. Well, this is fine if you want to do a quick analysis, but what if you want to preserve a trace that you want to look at later? Well, what we can do is go to a button that's unique to the scope and not on the graph display, and that is this button. It looks like the data selector triangle, the rainbow triangle with a little arrow shooting off of it. Watch what happens when I have a trace in the scope and I press this button. If you look over here in the data summary, you'll notice it took a snapshot of that particular trace on the scope. And I could rename this if I wanted to. I could rename this to something like short chime. All right. And that is now preserved as a set of data that I can refer to in the scope using the data selector button. I could choose short chime, or I could choose short chime and monitor run. So this data selector works just like it does in the graph. In this case, I'm looking at two of the same things, but let me turn it off for the moment so that I can collect another scope trace. In this case, I'm going to go to the longest chime and try to collect a nice waveform for that. So once again, I'll press monitor. The monitor run becomes the live data, and I can hit the chime again, the long chime this time, and when I get a nice trace, I will once again press stop. All right, so that looks pretty nice. I'm going to once again take that snapshot, and I can call this snapshot the long chime. And I could show both of them at the same time. If I wanted to see both of those, I can look at long chime and short chime, and we could begin asking what are some of the differences between these two. I heard a difference. I'm not sure if it came through with Zoom's noise canceling, but the short chime was definitely a higher pitch than the long chime. And here I can begin to do some analyses around that. So one thing I might ask is, well, what was the period of the short chime? Well, we have a coordinates tool in the scope, just like we did in the graph. I could drop that on one of the peaks from the short chime, use that delta tool, and figure out that the period of that looks like it's about 2.8 times 10 to the minus 4 seconds. If I wanted to convert that to a frequency, I'd probably pull out my phone and use the calculator there. But since one of the topics today is Capstone's calculator, I'm going to show you first how not to use Capstone's calculator. It works, but it's not really designed around it. If I open up the calculator, I could come in and say, what's 1 over 2.8 times 10 to the minus 4th? And there's a bunch of things here. Oh, sorry, 2.8 times 10 to the minus 4th. There we go. That's 3,570, so 3,570 hertz. Now, this is a bit awkward in the calculator, and we're going to see that the calculator does this, but it's not really designed around it. You'll notice it assigns that to a variable and lots of things, but at least I could figure out the frequency there. I could compare that to the frequency of the long chime, making that active, turning on another delta tool, and figure out that that has a period of 5.8 times 10 to the minus fourth, and 1 over 5.8 10 to the minus fourth gives me a frequency of 1.72. So we can do a comparison of those two with probably the same note, doubling of frequency between these two. So those are some quick tools. I want to show you one more thing about the scope before we move on, and that is you'll notice that these waveforms don't really line up. The scope display has some additional tools. I'll go ahead and just look at the monitor run. And one of the things we can do in the scope is to set a trigger so that this shifting of left and right doesn't happen like it does if I hit the chime. You'll see it's jumping left and right because it's just gathering data whenever it can, as fast as it can. We do have a tool here that allows us to turn on a trigger though. So now it's only triggering at a rising above 0. And now if I hit the chime, you'll see that it doesn't jump left and right as much because it is always starting the trace at a particular point. We can adjust the level of this, essentially using it like a trigger to capture something, or we can turn off that and it will start whenever, as fast as it can. So a little bit about that. Scope has capabilities much like a more traditional oscilloscope, including things like one-shots. So that's an introduction to the scope. We use the scope to try to figure out the frequency of these sounds, but as David has already intuited in the chat there is a way to quickly get Capstone to do the frequency analysis for us. I'm going to build a new page, so we're on page number 2, and I'm going to go back to the displays on the right side and open up an FFT display. FFT stands for Fast Fourier Transform, and if I choose for the y-axis my sound wave percent, you'll notice that the x-axis is always going to be a frequency, and this is basically going to do a frequency analysis for me. So we found the frequency of the chime in the scope. Let me monitor again, and I'm going to hit that and scale. All right, so here it's doing a fast Fourier transform for the short chime, and I can just come in and click and turn on a coordinates tool, and it tells me that that frequency is about 3,500 hertz. Similarly, I could do this for the long chime and determine its frequency. And you can see this can be a time saver compared to analyzing the frequency with the coordinates tool on the previous screen, but where this really comes into play and is valuable is let me make a more complex tone. Let me monitor and hit all 3 of my chimes at once. Let's see how complicated this scope trace is for this. All right, I see some patterns here, but this is a more complex signal. The real benefit of the FFT is the capability to come into the FFT, monitor all 3 of these. And there we can see it basically breaks it down into its component signals. So here are each of the 3 chimes at their respective frequencies. All right, so that's a quick introduction to the scope and the FFT displays, which are particularly useful when we're looking at fast signals and want to analyze frequency components of it. And again, some of the keys are the displays we choose and the fact that we are moving into fast monitor mode, which says you don't have to record all the data, just record the data as quickly as you need to fill the particular display or a trace on the display that you're looking at. All right. So we've looked at fast monitor mode and the scope and FFT displays. I'll pause here. And Alec, are there any questions we should answer as a group? I see you've answered some of them already here.
Yes, Scott asked how long is the recording time? I was just explaining in the chat that it's determined by the scale of the display.
Indeed, yep. So especially in the scope display here, it is going to just collect enough data to fill the frame of the scope display, in this case, just over 0.0025 seconds, as Alec just indicated. Thanks. Thanks for the question. All right. So if you wanted to take this further, you can use the scope display to essentially be a multi-trace oscilloscope. I could hook up 4 voltage sensors, say, to an RLC circuit, and the single scope display would let me look at the traces from both the voltage source, say a sine wave, over the inductor, the capacitor and the resistor, and in the single scope display, I could be looking at all 4 of those voltages and looking at the relative phase, for example. So that's one application of that scope display in fast monitor mode. Another kind of rolls it back and says, you know what, that FFT that does frequency analyses doesn't have to just be used with fast signals. It could also be used with mechanical systems that have modes, and we could determine those modes by looking at the frequency components of the motion. So in this case, we have some accelerometers on a shake tower, and we are looking at an FFT. You can see the frequencies are in the order of units of hertz, not kilohertz. And we can look at the acceleration and the modes for a particular floor on this shake tower. All right, so let us move on to Ohm's law. In this case, we're going to focus on output. So let me switch over here to show you the equipment we'll use for this. And for this one, we're going to take a look at the relationship between the current and voltage and current through some resistors. So I have a circuit board here. I could just as well be using bare resistors and some patch cords. But let's ask the questions, what's the relationship between voltage and current through a resistor? And begin by asking, well, how are we actually going to vary the voltage across that resistor? And in this case, the answer is going to be, we're going to use an 850 universal interface. And we'll have to figure out how to control the output of this 850 interface as we connect it up to one of these resistors. So we'll have the 850, which has some built-in output ports. I'm going to be using output number 1, and I'm simply going to connect that across one of these resistors. So let's head over to Capstone and create a new file. Turn off my sound sensor and turn on my 850 interface. Let's go to the hardware panel and see that the 850 is connected and detected. There we are. And I'm going to begin by hooking up the output from the output 1. So I'll use a red lead. And to begin, I'm going to go across a light bulb here for reasons that I'll demonstrate in a moment. So we're going to send a signal across this light bulb on this board from output 1 on the 850. All right, so the first question is, how do we actually vary the voltage? Well, let's go ahead and look at the signal generator panel. When you connect a device to Capstone that has the capability to have an output controlled by a signal generator, the signal generator button becomes available. And when I open that panel, we can see that it allows me to set the output parameters for all outputs on the 850. I'm going to stick with output number 1 here. And it allows me to choose waveforms, frequencies, and things like that. Let's start with the sine wave. I'm going to decrease the sample rate here to 1 hertz and increase the amplitude to, say, 5 volts, and figure out how can I actually get that signal to come out of the 850 across that light bulb. Well, it's not happening yet, and that's because the signal generator is off by default. But if I simply click on, you should now be able to see that blinking caused by that 1 hertz sine wave at an amplitude of 5 volts. All right, I'll turn it back off. There are other waveforms. I can actually choose DC here. So let me turn it back on. This is 1 volt. I can click it up to 2 volts, 3. I begin to see it getting brighter and dimmer as I change the voltage. So we can output DC voltages. I'll turn that off. What I actually want to do is output a voltage that slowly ramps up from 0 volts to, say, 5 volts. For that, I'm going to choose the waveform called positive up ramp wave. And this allows me to set the frequency. So I'm going to set it at 0.1 hertz. So it's going to take 10 seconds, and it's going to go from an amplitude from 0 volts up to an amplitude of 5 volts. So if I hit on, we should be able to see that ramping up, getting brighter and brighter, and then goes down to 0, ramps back up from 0 to 5. So that looks like what I'm looking for. I'll choose off. Now, I often use on and off buttons here to figure out if the signal generator is producing the signal that I want, if I can hear it through a speaker or see it in a light bulb. But when we get to actually experimenting, I'm going to choose the auto mode. What auto means is that whenever I'm recording data from sensors, the signal generator is going to turn on automatically. And whenever I stop collecting data, it's going to turn off automatically. So I have that now set to auto. I'm going to revert back to putting the signal across this physically largest resistor on the board right here. All right, and now we have to ask ourselves the next question. Now that we know how to get a signal across that resistor, how are we going to measure the voltage and current? Well, it turns out I'm not going to use anything that you don't see here already. I could go grab a voltage sensor, I could go grab a current sensor, but one of the talents of the 850 and 550 interfaces is that their outputs have built-in sensors. So this output that I'm using has some sensors built into it. I can access those by going to Hardware Setup and clicking on output number 1, where I can turn on different sensors. I'm going to turn on the output voltage and current sensor. And now I have measurements of voltage and current available, which I could place, for example, in a graph display. I'm going to plot voltage on the y-axis and current on the x. A little bit backwards, but we'll see why in a little bit. And now, because I have my signal generator set to auto, as soon as I hit record, we should be able to see the voltage and current across the light bulb being recorded by the built-in output sensors. So I'll hit record, scale to fit. There we can see it increasing, voltage and current. Go back to 0, and we'll let it do a full cycle here, which will take about 10 seconds, and hit stop. All right, so this is some evidence for a very linear relationship between the voltage and current across a resistor. So linear, I might be inclined to turn on a linear fit, at which point I can see the slope is about 10, and hey, no surprise, if I take this label off, we can see that that is a 10 ohm resistor is labeled on this board. Well, let's try a couple other things. You might have noticed it started in the middle. That's just how the output starts for a ramp up wave, but I can come in here to the signal generator and I can offset it by 180 degrees. So now it's going to start at 0. And to save myself a little trouble, I might want to have it stop automatically just before it reaches as 5 volts. So let me go to recording conditions down in the controls palette, and I'm going to choose a measurement-based condition so that when the voltage is rising above, say, 4.9 volts, it's going to stop automatically, so I don't need to remember to do that. So let us switch from this large physical resistor to the next smaller, physically smaller resistor. And I'm going to turn on the data selector button so we can see both runs at the same time. I'll hit record. And here we can see a linear fit to this new set of data, voltage versus current. Looks like it has a slope of about 33, and no surprise, that's a 33 ohm resistor. So we can collect some data here to get some understanding of the linear relationship through a resistor, at least, of voltage versus current. Now we might challenge our students and say, well, what do you think would happen if I added another patch cord here and I put these two resistors, say, in parallel? And Capstone's graph gives us a nice tool for challenging our students to visually indicate what they think will happen. That's the prediction tool. So maybe I think these are going to split the difference. Say I'll make a point-by-point prediction that I think if I have them in parallel, I'm going to get something like that in between the two resistors. Well, let's check it out. I have these in parallel now. I'll go ahead and hit record. Nope, I connected the wrong ones. Sorry. Let me go ahead and just delete that last run. I have to go across the 10 ohm and 33 ohm. There we go. All right, so my prediction was a bit off, but it looks like because we have these two channels here, the effective resistance is lower when we put the two in parallel. All right, so you can see the sorts of explorations we can do with the output of the 850 and these built-in voltage and current sensors. Let's make it a little more interesting though. I'm going to ask the next question, which is, well, we've investigated various resistors and combinations of resistors. What would happen if we had a light bulb? So let's head back here, and I'm going to get rid of one of these cables and just go across the light bulb built into my board here. I'll turn off the data selector button here, so we're just going to get a trace of the new run. And remember, it's going to start at 0 volts and go up to 5 volts. So in your mind, make a prediction of what you think this is going to look like. Is it going to be just like these resistor straight lines or something else? And there it stops just short of 5 volts. Turn off the prior prediction here. And here we can see for the light bulb, I'm getting maybe two linear domains, but it's definitely not a linear relationship like the one we saw with the resistors, the simple resistors. So something is happening here. Now, I don't know if you're watching the live video here, but you might be wondering what was happening when this little blip happened. What caused these two domains to be separated like this? Now, a lot of times we have questions where wouldn't it be nice to have a dash cam in life? And Capstone kind of allows that. I have a webcam here, that pointing at the board. And I'd like to do this again, but I'd like to have a live video recorded alongside this data so that I can review it and say, well, what was happening when we got this little change in signal? So I'm going to drag out a movie element. I'm going to make it pretty small here. And I'm basically going to tell Capstone to fill this movie element with video and sensor data. Here is my USB webcam. And I'll position this here and turn off the audio. There we go. And I'll turn off the light as well so we can see this light bulb. And I'm simply going to press record again. And whoop, stop. Get rid of that extra run. And now we have the playback mode where we can basically scrub through and we can see that that transition, oh, sorry, collect another one here. That transition appeared to happen when the light bulb began to glow. That should be enough there. So in playback mode, we can scrub through and see that I have it fairly linear until that bulb gets brighter, at which point the bulb has a different effective resistance. All right, so that ability to have a movie synced with data is a great way, especially in mechanics and any visual sort of experiment, to connect the real world visual information to the data collected from sensors. I'm going to delete that for now so we can scale this graph. And let's take a look at this data now. Previously, we had very simple graphs, linear relationships between voltage and current for a resistor. But in this case, I'm having some nonlinear relationship, and I might want to still have some concept of the relationship between voltage and current being a resistance. This time, though, it's not as simple as a slope. One way I could do this is to turn on the coordinates tool. And if this point were 0, 0, I could say that if resistance is the ratio of voltage to current, then I could turn on a delta tool, and I could take this delta tool and not look at the values of the delta, but right click and choose to look at the slope. This is basically the slope of that dashed chord line, and this is the resistance at that particular point. And I can use my keyboard here to scroll through and see that the resistance is a fairly constant 6.9 ohms in the initial part, and then it fairly rapidly increases as that bulb turns on, and it continues increasing here up to, well, when I stopped, it was closer to 20 ohms. So this is a nice way to be able to figure out graphically the resistance rather between these two. But wouldn't it be nice if I could just get Capstone to do the work for me? And that's going to be our introduction to using the calculator in the quote correct way by transforming data measurements, combining them. So how can we determine a new indirect measurement, resistance, from the direct measurements we've made of voltage and current? And to do that, we're going to go to the calculator. And we're simply going to define a calculation that's going to take inputs from data sets that are recorded and produce an output. And the syntax for this is to indicate the output and then an equal sign. I could call this output anything I want. I could write out resistance. I'm just going to abbreviate it R. And I'm going to define that as V divided by I. I'll hit enter. And this is going to be in ohms. So I'll right click, insert special character. And what is the voltage? Well, the voltage is not a single value. It is all the measurements coming from the voltage sensor. So I need to be able to define an entire array of data. The way I do that is to come down to the data selector button, where I can see that I can choose different measurements. I'll choose output voltage for voltage in volts. And for current, I'll go back to the data selector and insert the output current in amps. Now what's going to happen is this calculation is going to take every voltage and every current input and output a new set of data that is R, or resistance. How can I see that data? Well, it's available in any data display just like raw sensor data is. So I could add a new plot area and make this a display of the resistance. And if I scale to fit, let me double check that calculation. Looks okay. Let me collect a new run of data here. One of the powers of the calculator is the fact that it works live. So this calculation on the bottom of resistance is a live calculation based on combining those streams of voltage and current data. All right, so you can probably imagine many different applications where you have some data coming in from a sensor and you want to transform it. It could be as simple as subtracting an offset from a force sensor measurement, or as complex as looking at the ratio of two different measurements. So Boris notes differential versus average resistance. Yeah, if we want to talk about the concept of differential resistance, then we might, for example, turn on a slope tool to this plot of voltage versus current. And that tangent line is what some people call the differential resistance. In this case, though, we're actually looking at the resistance at a point, either by looking at that chord slope that we looked at graphically earlier, or by doing this live calculation of the resistance as the ratio of voltage to current. All right. So that's Ohm's law. I'll note that this signal generator, one of the key things we've learned about, is available for many different output devices from PASCO. We looked at the 850 and its 3 outputs. There's a new accessory, the expansion board for the 850, which can output those outputs to a board on top of the 850. The 550 interface has a single output that can be controlled, and we also have a function generator that can actually be hooked up to Capstone and controlled via the signal generator. And if you want to stay in the wireless world, the AC/DC electronics module for our modular circuits can be controlled by the signal generator. All right, so that's the signal generator using the output measurements built into the 550 or 850 and a better introduction to the calculator. Alec, any questions we should address before we move on? I see you've been busy answering them in the chat. Anything to bring to the attention of everyone?
One question. Chris brought up the question of when you would use the internal voltage sensor versus an external one.
Yeah. Yep. So I think Alec got it there in the chat. So in this case, we have a pretty simple circuit where we just have one element, and we're interested in just the voltage across the outputs is equivalent to the voltage drop across the in this case the light bulb. So I can equate the two, assuming that these wires are very low resistance. But as Alec noted, if we were back, say, in this example, where we wanted to look at, well, let's take this specific example. I could look at the output voltage across the output itself. I would use the output sensor, and then I would actually probably do this experiment with 3 discrete voltage sensors, one across the inductor, one across the capacitor, and one across the resistor. All right, thanks for the question. All right, anything else, Alec? Thanks for keeping on top of those. All right. So if you want to take it further, these concepts we've just introduced, well, you can actually automatically sweep across different frequencies. I could manually adjust the frequency, say in an LRC circuit, or we didn't look at it, but there is a sweep available for waveforms like the sine. And if you turn on, say, a single sweep for the sine wave, it gives you the opportunity to set an initial frequency, a final frequency, and the duration over which that sweep would occur. So in this case, when I pressed record, if it were in auto mode, this output signal would start at 10 hertz, and over 5 seconds, it would increase to 100 hertz. And this could be useful for finding resonance, say, in an LRC circuit, or hooking this output up to a speaker and finding the resonance in, say, an air column. Now, I didn't mention this, but if we look at the signal generator, you'll see these calculator symbols throughout. Instead of specifying a constant, say, frequency, we could actually use a calculation to indicate what the frequency should be at any one time, what the amplitude should be. Here's one example where I have a temperature sensor in a little house that's over a light bulb, essentially a thermostat. And I could use, say, a DC output and define a logic statement in a calculation that says, turn on the DC output to 4 volts if the temperature reading from a sensor is less than 20, in this case, degrees Celsius. So the calculator can be used as a controller for the output of the signal generator parameters. Or what I find more easy to do is Capstone has Blockly code built in, so I could write the same expression in Blockly code, which I find easier to read, and control outputs from any of those interfaces we just talked about via Blockly code. All right, so we're moving into our final activity, and in this one we're going to set aside the sensors, we're going to set aside the interfaces, because we're going to do some data analysis based only on a video. So the question here we're going to answer is, how much data can I get from a video? Let's take a look at the video. So I'll go ahead and play this video, and we'll talk about the characteristics of this video later, but let's just take a look. And as you're looking at it, think about some of the questions you or your students might have about how the ball moves in this video. So let's go ahead and play this. All right, so a few seconds of video. I'll play it once more and ask yourself, what sorts of questions would you and your students have about the motion of the ball that we might be able to investigate if we can turn the motion in this video into data inside Capstone? All right. So if you have any thoughts, go ahead and put them in chat. What questions do you have about the ball's motion that we could try to do video analysis to try to answer? All right. And fundamentally, as we get started here, we're going to have to start by answering the questions. If we have a video that is essentially pixels, how can we translate information about pixel locations into the real world distances that we need to do some physics? So in the chat, go ahead and suggest some questions you have about the ball's motion that might be fertile for us to analyze once we figure out the basics of translating from pixel locations to real world distances. So back in Capstone, I'll go ahead and turn off my interfaces, choose a new experiment. And this time around, we're not going to hook up anything for hardware setup because all we need is that video file that I recorded. So I'm going to go over to the displays, and one way to do this is to find the video analysis display. I'll double click on that, and I'm going to open that movie file that we just looked at in the slideshow. This is just an MP4 file off of the camera. Open that up, and there's the same video we saw on the slide. So David, thanks for your thoughts here. We could ask, what is the acceleration of the ball horizontally? What is the velocity of the ball vertically? Two great questions that we can get at here. So keep those questions coming. Thank you. So here's the video. And if I'm in playback mode here in the controls palette, I could play it back in Capstone. We'll just watch it one more time here. And I understand it's going to be a little choppier through Zoom than it is for me, but that'll be remedied when we go frame by frame in a moment. So let's get to that question of how do we translate from real world distances or to real world distances from these pixel locations that we have. So one thing we need to do is figure out what our coordinate system is. And you'll notice that as soon as you bring in a video and video analysis, you have a coordinate system defined here, and I can move it anywhere I'd like. So I'm going to set the origin just at Susan's toe here. And I can see X going off to the right, Y going vertically. If I hadn't leveled the camera, I could remedy that by just rotating it here, but I did a pretty good job of leveling, probably with a bubble level, so it looks like that's all set up. Philip adds the question, what's the coefficient of restitution for the ball's collision with the ground? That's an intriguing one as well. So I've defined my coordinate system, and by the way, I can change this at any point during my investigation if I found it more convenient to put it elsewhere. This is just our starting coordinate system. The other thing I need to do is translate from this being some hundreds of pixels to the right and down into some position in the real world relative to our origin. The way to do that is to notice that I have a calipers tool here, and I can drag out this caliper, and what I want to do is put the ends of the caliper for a known distance in the real world. I happen to have put a meter stick here right next to the ball's plane of motion. So I'm going to grab the calibration tool, this caliper, and put it at one end of the meter stick right there, and grab the other end and put it at the top of the meter stick. And if it was a 2-meter stick, I could come in here and change that, but it was a 1-meter stick, which is the default. So what I've done now is defined how many pixels represent a meter in the real world. Yep, David, yep, one step ahead there. All right, so I've now defined a coordinate system. I've defined a translation from pixel dimensions to real world dimensions. And now what we're going to do is figure out where the ball is at each time here. So we have positions handled. What about time? Well, when this movie came in, Capstone read the movie file, the movie's metadata essentially, and you'll notice that it determined this movie was playing back at 29.97 frames per second. An odd one in most of the world, but that's the NTSC North American frame rate by default, and it properly interpreted that. So this is how it's going to get the time information. It knows that from one frame to the next is 1 over 29.97 seconds. You could change this if, for example, you had slow motion footage that was redefined incorrectly. So I'm going to go to a location where Susan has released the ball right about there. And all I need to do is take my cursor, go out and find a spot on the ball that I can identify. I'm going to choose the center and I'll click on it, and it deposits a crosshairs there to indicate that it has recorded the position of the ball at that time. And by default, it advances one frame ahead, which is handy, so I could click again. Now, here are some tools that can make it easier to do your analysis. I could put a magnifier on and use my scroll wheel to zoom in, and this gives me a much better chance of identifying the exact center of the ball to be consistent. So I'll click there, I get another crosshairs. And what's happening behind the scenes? Well, if I drag out a table to the right of my video analysis display, I could choose to look at, say, time and object one's X position. And each time I add a crosshairs, notice that it is telling me that's the time at which that event occurred, that frame occurred, and this is the X position of the ball. So I could go through and do this, or since we don't have much time, let me see this. I can enable auto tracking, and I'm hopeful here, if I turn off the magnifier, this gives me a circle that I can adjust to surround the object I'd like to trace. And fingers crossed, if I hit start, I'm hoping that Capstone can do the work for me and basically drop all the crosshairs on this ball each frame by frame. I'll press start. It seems to be doing a pretty good job here. It'd be a good test when it hits the ground to see if it can ignore prior progress. There we go. So notice it's doing the work for me, and we can see that table filling up with time and position values. I'm going to stop it just before we get to the edge of the screen, because once there's no ball here, it can have a lot of trouble figuring out where the ball is when it isn't there. So I'll press stop right now. And I think that's enough data for us to begin answering your questions. So I'll hit done. And now we have 115 data points here where we have the time, and look at all this data. We have the object's X position, Y position, X velocity, Y velocity, X acceleration, Y acceleration, etc. So I'm going to go to a new page here, build a new page, and we're going to begin to take a look at some of those questions. I think David was asking some questions about velocity of the ball vertically. So here's a trick. I'm going to go back to page 1. I'm going to click on the border. Oh, undo that. Click on the border, so edit, copy. I'm going to go to page 2 of my workbook, choose edit, paste, and that's a nice way to replicate that display so I don't need to redo it. And this time around, I'm going to drag out a graph on the right side and give it a bit more space than the table had. And let's go ahead and let's try something simple. What if the x-axis is the object's X position and the y-axis is the object's Y position? Well, go to playback mode, maybe half speed. I can now play this back, and we should essentially get a map of the ball's position, right? I can scale to fit. That looks pretty good. On to David's real question, though. What about velocities? So let me change the y-axis to be the ball's y velocity. Scale to fit. This is getting more interesting. So let's play it again. This is again half speed. You can see the velocity changing rapidly each time it bounces, but it's pretty consistent between the bounces. And we might have other questions like, well, what about the X velocity? And if I choose the y-axis and add similar measurement, it knows that both of those are velocities, and I can simultaneously look at the X velocity in purple and the Y velocity in orange. So if we want to begin to talk about the independence of these two velocities, this is a nice way to begin illustrating that. There are some changes here when the ball hits the ground. We can talk more about that, but you can see how much data we're beginning to be able to extract here based simply on these positions of the ball over time. Now there's some additional good questions. Coefficient of restitution. We could look at the heights of the successive bounces to try to answer, I believe, Philip's question. So lots of questions we can answer. I want to veer over to another question, though, and that is, what is this ball's energy? All right. What is this ball's energy? So if you wish to participate here, you can go to this address. Alec, would you mind pasting this in? It's bit.ly/ball energy. And this is going to be a Google drawing that will allow you to select the scribble tool and make a sketch, just a rough sketch, of what you think we're going to discover when we calculate the ball's gravitational potential energy and add that to the ball's kinetic energy over the course of this video. So if you go into this Google drawing, you'll be able to choose this tool, the scribble tool, and I'm just going to draw a smiley face here, but you'll be able to draw your prediction over time on this graph. And again, that's at bit.ly/ball energy. Thanks, Alec, for pasting that into the chat. Fantastic. So don't be shy, you're anonymous, I believe. Go ahead and make a sketch, just a rough sketch over time. What do you think we're going to discover for the sum of gravitational potential energy and kinetic energy? Cool, we'll revisit that in a moment, but as you add your sketches there, let us figure out how to do this in Capstone. We don't have an energy calculation built in. We have the ball's positions, we have its velocities, but we know from the definitions of gravitational potential energy and kinetic energy that that should be sufficient information. So let's go to our powerful calculator here. And once again, I'm going to define a new calculation. It's going to be GPE for gravitational potential energy. What is that? Well, that's mgh. I'm just going to put in those variables, and the units will be joules if I use the right units for the inputs. What is mass? Well, I put this ball on a scale and found it to be 0.575 kilograms. G, I'm going to right click, rather I'm going to insert here a constant. It's built into Capstone, acceleration due to gravity. That's in meters per second squared. And finally, the interesting input is the height. Well, what is the height? Well, that is fairly direct, right? That's just the y position of the ball. So if I come here to object 1, that is its y position, and that's in meters. And now if I return to this graph, I should be able to change its y-axis to display the gravitational potential energy. I'll scale to fit. Let's see if that makes sense as we play back the ball's motion here. It's looking good. Of course, that's going to correspond to its y position, so that's pretty straightforward. Let us now return to the calculator and ask something a little more complex. How about kinetic energy? Well, straightforward, that is 0.5 or 1/2 times mv squared. And that'll be in joules. Notice it didn't ask again for m because that's previously defined, but it did ask for v. So let's think about this. What is the velocity of the ball? And how can we get that from the measurements that are given to us from this video analysis? Well, if we look at the measurements we have here for the object, I have an x velocity, I have a y velocity. Which one should I choose? Well, if we think about it, the velocity we actually want is the resultant of these two components of velocity. So what I'm going to do is say, you know what, I can just take the square root of the squares of those components, and I should be able to get the instantaneous velocity of the ball. So there's square root, and I'll insert the x velocity and square it, and add that to the y velocity and square that with caret 2. And that's going to be in meters per second. All right, so fingers crossed, I'm going to go to the y-axis here, add similar measurement, same unit, so I can add that. And there is the kinetic energy in green. Let's play that back and see if it makes sense. Slower, faster. That seems to kind of reflect the gravitational potential energy. We should have some relationship between those two. And if we look at our sketches here, we have some predictions. Again, this is the prediction of the sum of the two. Do we think we're on track for some of these? The steps seem to be promising. Let's go ahead, though, and figure out finally this question. What if we want the sum of those two? I'm going to call it E sum, and that's simply GPE plus KE in joules. And you can see how this calculator is allowing me to basically build more and more complex calculations of measurements that we don't have direct sensors for. So let me add a similar measurement here, and ultimately here in red, we have the sum of those two forms of mechanical energy. So let's see how that evolves. The stairs, definitely, we're noticing those stairs, and if we were listening to the video, we'd hear sound and might be able to explain that loss of energy from step to step, as some of you illustrated here in your predictions. Does anyone notice anything interesting, though? I don't think anyone predicted some small behavior here, even those of you who had the steps. What do you notice about the sum of those two forms of mechanical energy here? That is the red plot. Meanwhile, Patrick asks, clearly struggling to pick up the zero well on the second bounce. Is that typical? I assume that's the zero position right here. Yeah, so there are a couple of factors at play here. One could be we're at the center of the ball, so we'd probably not expect it to ever go exactly to zero, but these two bottomings might indicate that it can get pretty close to zero, if we're looking at position, of course. The other thing that's happening is we only have so many frames. This is about 30 frames a second, so we might actually be missing the ball when it is near that second bounce. Let me go frame by frame here, and we can see we might not actually have data points for that moment in time. Although, since the ball is stopped when it's hitting the ground, we should have a slightly greater chance. You notice it looks there like the ball hit the ground, and then we got it going down and back up, but never on the ground itself. Great observation, though, Patrick. All right, well, I don't see anyone noticing it, but notice these dips. The sum of gravitational potential energy and kinetic energy definitely goes flat during the first arc, and it's lower but flat during the second. What in the world would cause this to dip below that step height between the two? I'll leave you to think about that in the chat, and we'll revisit. If any of you have suggestions, feel free to send it in chat. In the meantime, though, before we revisit that, let us review. We figured out video analysis. One thing I haven't showed you is the fact that when we were talking about the x and y velocities, we could come in here into the settings and actually turn on vectors. So I'm going to turn on the velocity vectors for every data point, and I'm going to make them a little bit longer. And if you wanted to begin to illustrate how the x and y velocities change, the video analysis tool also allows us to turn on these or acceleration vectors, where we can see those vectors at every data point and see that the x velocities are fairly consistent, whereas the y velocities, of course, go from positive to negative. Christopher has a thought here: stored elastic potential energy. Indeed, so there are some forms of energy that we are not capturing here in our calculation. We are not capturing the fact that this ball compresses, and as Christopher says there is stored elastic potential energy, some of which you can see we're getting back here. Cool, thanks for your thought, Christopher. All right, so we've looked at video analysis, vectors, more calculations, and one final thing to wrap it up. If we looked at this graph, it can be a little hard to follow. So Capstone actually has a relatively new display called the bar meter. And if I want, I could come here and say, you know what, this bar meter is great for looking at live values. And I could compare gravitational potential energy, kinetic energy, and the sum of those two, which I didn't call total energy because we were missing some things. And I could play those back and look at either the graph or the bar meter, and you can see the exchange between those different forms of energy and the sum of the two decreasing bounce to bounce. All right, great. So if you want to take video analysis further, you can record your own videos for analysis. We're at the end of time here, so I will share some good characteristics of videos, but if you have any real world suggestions, observations about videos, please share them. As Chris notes, yep, it looks exactly like that Fed Energy skate park, doesn't it? But the real world. Another capability that's not well known is the video analysis tools in Capstone can be used to analyze still photos. And we have a video on that. Alec, if you could kindly paste that link, you can get a quick video showing you how to use these similar features for photo analysis, in this case, finding a catenary equation from a suspended string. So what makes for a good video for analysis? You might have already caught some of these characteristics. The camera is stationary and it's level. The object is moving parallel to the plane of the camera sensor. That is, it's not coming toward or away from the sensor. And that's crucial because we need to be able to know what the dimensions of that object are and what the location of the object is in its plane of motion. So you'll see all those characteristics are true in this case. We have a ball moving in the plane of motion, which is parallel to the sensor or perpendicular to the axis of the lens. We have an object of known length, the meter stick. The moving object is not blurry. This is probably the most subtle of these characteristics, but if you noticed when I was doing the manual analysis, even when this ball is moving fast, it is not a blur. It is what looks like a solid ball. Now this blur I'm talking about is not so much a focus blur, but just the blur of the shutter being open for a long time during the ball's motion. So if you can, and you have manual controls, set the manual controls so your camera has a fast shutter speed. In the video you just saw, it was 1/1000th of a second that the shutter was open, ensuring that that ball was just a stationary object with not much movement during the shutter being open. Another thing you can do if you don't have manual control is bright lighting. And the brightest lighting we can get is outdoors, so it's a great way to use the sun's energy here to ensure that your shutter speeds are fast. And finally, for auto tracking, you want to have the object be distinct from the plain background. All right, well, that's going to formally wrap it up here. If you have further questions, I encourage you to get in touch with your local PASCO rep. We have reps around the world and across the US. You can find your local rep at pasco.com/support. You can also find technical support's contact information there. I want to thank you so much for joining us today, and we hope to see you at a future webinar.